Hello students, welcome you all. In pericyclic reaction, today I will prove this sigmatropic rearrangement by frontier molecular orbital method. Now in my previous lecture, I gave you the introduction of sigmatropic rearrangement, in which I gave you various examples of sigmatropic rearrangement, and we analyzed the sigmatropic reaction by taking the reaction into the radical form. Now let us prove this sigmatropic rearrangement by frontier molecular orbital method. Now FMO method, that is frontier molecular orbital method, or analysis by frontier molecular orbital method. Now what was the rule that we have found out? So for hydrogen shift, the rule was for hydrogen shift. What was the rule? Under thermal condition and under photochemical condition, for 4n electron system and for 4n plus 2 electron system. For 4n electron system, under thermal condition, intrafacial interaction. For under photochemical condition, suprafacial interaction. Here supra and here intrafacial. This we have analyzed in my previous lecture. Now let us prove this selection rule by frontier molecular orbital method. We know that in frontier molecular orbital method we take two component, one component, we divide the whole molecule into the two component, and one is taken as HOMO, another is taken as LUMO, and vice versa. So here in FMO method, what we do, one component is HOMO, other component is LUMO. It is taken as LUMO, or vice versa, we may take vice versa, either this one, this may be taken this one, or this may be like this. Okay, now let us see for 4n electron system first. Okay, now for 4n electron system, suppose if we have, this is an example of a 4n electron system where 1, 2, 3. First of all, what I have told you, we should give the allylic carbon is given number 1, 2, 3, and the atom which is attached to the allylic carbon is also given number 1, and the new bond is formed between 1 and 3. 1,3 shift has taken place, and we get this thing like this, new bond over here and new sigma bond over here. This is the new sigma bond which is formed between 3 and 1, and this was 1, 2, 3. Now in FMO method, what I have told you, one component is taken as HOMO, another component is taken as LUMO. So if you will see here, suppose what I take this one, this is our first component, which is C double bond C bond, and this is our second component, which is CH bond. This is our CH bond. Okay. Now under thermal condition, what we can write? C double bond C bond. This is, suppose I take it as a HOMO, and CH sigma bond is taken as LUMO. So HOMO of this alkene type of system, ethene system, that is, all of you know, this is our pi is the HOMO, and LUMO for this is sigma star is the LUMO. Or otherwise we may take in another opposite manner also. This may be taken as LUMO, this may be taken as HOMO. If I take it LUMO, then it would be pi star. If I take HOMO, this would be sigma. Then result that come out to be same. Okay, in both cases result will come to be same. Now if this is HOMO, then what I should write, suppose this is our C single bond C, C double bond C, and if this is our HOMO, this is HOMO, that is pi, and then it would be plus plus, and this is minus minus, plus this is C double bond C. Now it is attached to this bond. This is suppose 3, this is 2, and this is our 1. And now CH bond is LUMO of CH bond. So LUMO of CH bond plus minus, and this is our CH bond. This is H plus minus. So this represents the sigma star like this. This represents the sigma star. 1 1 1 1. So this bond will break. This bond breaks and it will form bond with this third carbon atom. Now if you will see in this case, then here the interaction, if you see the suprafacial interaction, if you see the suprafacial interaction, then this will interact with this lobe and this lobe. These are the two same side lobe of ethene system. It will interact with this CH sigma bond, bonding interaction over here, and this will also form a bonding interaction over here. This is forming the anti-bonding interaction. So suprafacial interaction is disallowed over here. So supra is disallowed. Supra is disallowed under thermal condition. So what is the rule? Under thermal condition, intra is allowed. Intra is allowed. Now let us see for intrafacial interaction. Intrafacial interaction. Okay, so again this is third, second, first, and this is also first. First will form a bond with third. So intrafacially means intrafacial, different opposite side lobe that will interact. If this is this lobe, then another interaction would be this would be the another interaction. So this is intrafacial interaction. So here this is bonding interaction. Here also it is the bonding interaction. That's why intra is allowed. Intra is allowed here. Under thermal condition, intra is allowed, that we have seen over here. Now under photochemical condition, if you will see under photochemical condition, now C double bond C bond, that would be the HOMO of C double bond C bond under photochemical condition, that would be pi star. That would be pi star. And LUMO would be sigma star only. Under photochemical condition or under thermal sigma star, as well as under photochemical condition also the HOMO would be, the LUMO would be sigma star. So this is our HOMO under photochemical condition, and this is the LUMO under photochemical condition. Now, so C double bond C is pi star. C double bond C is here pi star. So pi star means plus minus. So this is our HOMO, C double bond C, HOMO, pi star. So I should write pi star over here, plus minus, this is minus, this will be plus. Now this is our third carbon, this is second carbon, and here this is our first carbon. First carbon is attached to one of the hydrogen, and this is first one hydrogen. So this is sigma star. This should be sigma star. CH should be sigma star. So sigma star means plus minus. Sigma star means plus minus. Now interact. Let us see the interaction in a suprafacial manner. So if you will see, suprafacial means same side lobe of this and C double bond C that will interact, and same side lobe, and you can see the bonding interaction. Here also bonding interaction. So supra is allowed under photochemical condition. Supra is allowed under photochemical condition. It is allowed. And if you want to see under in intra, then intra will not be allowed under the photochemical condition. So let us see whether intra is allowed under photochemical condition or not. Okay. Now interaction will be from the opposite lobe. Opposite lobes will interact. Now this opposite lobe will interact. So this is bonding interaction, this is anti-bonding interaction, and this is disallowed. So intra is disallowed over here. Clear? So this is the case for 4n electron system. Now if you will see for 4n plus 2 electron system. Now let us see for 4n plus 2 electron system. (4n plus 2 electron system). Now so first of all, give the numbering. Allylic carbon is given number 1, 2, 3, 4, 5. Atom which is attached to allylic carbon atom is also given number 1. This sigma bond will break as it gains the energy. Such kind of migration will take place, and here single bond, double bond, single bond, double bond, and here the migration is taking place at the 5th position. This hydrogen is coming at the 5th position, 4th, 3rd, 2, 1, like this. Okay. Now, so if you want to see this rule, then by FMO method. So one component is taken as the HOMO, another component is taken as a LUMO. So in here two component, how you can divide two component? This is one of the component, butadiene, and this is the other component, CH bond. So two component are, one of the component is butadiene. Butadiene is one of the component which I may take it as a HOMO. The HOMO of butadiene under thermal condition. So first of all, under thermal condition, butadiene is HOMO, and CH single bond is, I will take it as a LUMO. So if HOMO of butadiene is Psi 2, and CH, that is sigma star, is the LUMO for this CH bond. Okay, so now let us see how we can show it. So this is the 4 orbitals of this butadiene, and Psi 2, that is HOMO of this butadiene, I should write, and that is Psi 2. That is, Psi 2 means even molecular orbital, and for even molecular orbital, what I have told you, the opposite lobe that should have the different sign. Now this interacts with, this is our CH bond. So if this is our 5, this would be 4, this is 3, this is 2, this is 1, and positive, and LUMO, because this is LUMO, then this is positive, negative, this is sigma star. Now let us see the interaction in a first suprafacial manner. So in a suprafacial manner, this interacts with this one, and this interacts with this one, and as you can see here bonding interaction, here also bonding interaction. That's why this is supra is allowed. Here supra is allowed. Now if you will see for intra, whether intra is allowed? No, intra is not allowed. Intra is not allowed. You can see. Again, positive, this is negative, this is positive, this is negative. This is sigma star, this is our side 2. And if you will go for the intra, means opposite lobes should interact in a intra. So now this will interact to form a bonding, but here this will interact to form a anti-bonding interaction. This is anti-bonding interaction, this is bonding, this is anti-bonding. So anti-bonding interaction is disallowed. So that's why intra is disallowed. Intra is disallowed. Here. Now in the same manner we can prove for second case, that is here intra, what I have told you, under thermal condition only supra is allowed. Only supra is allowed, intra is not allowed. Now for thermal photochemical condition, the butadiene homo of butadiene, that becomes psi3. That becomes psi3. Already I have given you the lecture on this molecular orbitals and this homo, LUMO and the symmetries. Already I have given the lectures. So CH sigma bond, this is LUMO, and LUMO for CH sigma bond under photochemical condition, this will remain same, that is sigma star. So under photochemical condition LUMO would be sigma star. Under thermal condition LUMO is sigma star, and under photochemical condition also the LUMO of CH bond, that will remain the sigma star. Now first of all, for butadiene, these are the 4 orbitals of butadiene, and psi3, for psi3 the end orbital that should have the opposite sign, plus minus. And suppose this is 5th carbon, this is 4th carbon, this is 3rd, this is 2nd, and this 2nd, the 1st carbon, and this 1st carbon is attached to the hydrogen, and this bond is the sigma star. So for sigma star we should write plus minus. So this is our 1st carbon, and this is attached to this 1st carbon is attached to this hydrogen, which is also given in the number 1. So this breaks, and 5 bond that should get formed. Now if it interact in a suprafacial manner, whether it is possible in a suprafacial manner, let us see bonding interaction. Here also in a suprafacial means same side lobes interact. In a suprafacial interaction, same side lobe interact. In an interfacial interaction, opposite side lobe interact. So what you can see, both are the bonding interaction. That's why this interaction supra is allowed over here in photochemical condition. In photochemical condition for 4n plus 2 electron system, the so this is actually plus psi3 means end orbital should have the same sign, and this will be minus. Okay, now if you will see the suprafacial, then anti-bonding interaction is taking place over here, anti-bonding interaction, and that's why supra is disallowed in this case. Supra is disallowed, means intra should be allowed. Intra is allowed under photochemical condition for 4n plus 2 electron system. So now let us see for intrafacial interaction. End orbital is having the same sign. Okay, now intrafacial interaction, these 2 lobes should interact. So these 2 lobes should interact. One is interacting with this one, and another interacting in this one. So this is our bonding interaction and this is our anti-bonding interaction. So bonding interaction and bonding interaction. That's why intra is allowed. Intra is allowed. So this is, thus we have proved the this sigmatropic rearrangement by FMO analysis. Now in the same way we can prove for the alkyl shift also. In the same way alkyl shift that can be proved. I have given the selection rule for the alkyl shift and analysis of this alkyl shift by the radical approach that I have already told you in my previous lecture. You may go through it in that lecture. Now let us see few examples. Now if you see the example, then now suppose if you have now what should be the product of this reaction? What should be the product for this reaction? Let us see this one. Now, first of all, what I have told you, in such reaction, in sigmatropic rearrangement, first of all, we should give the numbering, and allylic carbon, that should be given number 1. So if this is 1, this would be 2, and this is given number 3. And now from this first carbon, allylic carbon, the another which is group or atom is attached is, this is the another group or atom which is attached. Suppose I give it number 1 dash. And we know that in sigmatropic reaction 1-1 bond break, and here the 3-1 bond should get formed. 3-1 bond that should form. Now which bond that should break over here? Here this bond should break. This bond that should break. And new bond that should be formed between 1 and 3. This bond will get formed. So how you can draw, how you can rotate this bond will rotate like this. So if this is formed, then here this valency of carbon will get increased, and now this bond, this sigma bond break, and it will form a new bond at this position, that is third position. Okay. Now, so if you will write here, then now, so new bond is formed between first, and new pi bond is formed between first and second. And this 1-1 dash is broken down, and this remains same. This remains same, and new bond is formed over here. That is third. This is second, and this is first. Suppose, and new bond you will see. This is the new bond which is formed, and here. This is your OAC acetate group is present over here, and the hydrogen is present over here. Now what about the stereochemistry? Now what kind of shift? This is not the hydrogen shift. This alkyl group is shifting. The shifting of alkyl group is taking place, and for alkyl shift I have already given you the rule. What was the rule for the alkyl shift? For 4n electron system and for 4n plus 2 electron system, the rule that I have told you, superficial with inversion, or interfacial with retention, or superficial with retention, interfacial with inversion and write down diagonally in the same manner. So this is the rule that I told you for alkyl shift. This is the rule. Now this is an example of 4n electron system. How many electrons are involved in this reaction? These 2 electrons, they are participating in the reaction, and this sigma bond electron, they are participating in this reaction. So this is an example of 4n electron system. This pi bond is involved in this reaction and this sigma bond is involved in this reaction. CC sigma bond is involved in this reaction, and shift is the alkyl shift which is shifted to the 3rd position. So this is here, this is shifted. Now, so what should be the stereochemistry of this substituent which are present on this carbon? So because this is 4n electron system, under thermal condition, suprafacially it should interact with a inversion of configuration. The same side suprafacially, but the stereochemistry of this will get inversion. So inversion of this alkyl group that will take place over here after superficial migration. After superficial migration, inversion that should place. Here deuterium is on the left side, that's why it should go on this side, and this will go on this side. So it will go at the right side and hydrogen is going on the left side. So this would be the case for this one. Now we can also show it in another manner. We can show it. Suppose this is 1, 2, 3. If it is 4, 5, and suppose this is 6, this is 7, and we may show it in another manner like this. If you will see, and suppose this is our first carbon, second carbon, and this is third one, fourth and fifth, and from fifth, this is first, second, and suppose this is third, and this is fourth, and this is fifth one. So we may show it in this manner. This bond, this is our first, second bond, and here fourth. This is the fourth one. This is fifth one, and this is our first, second, third, fourth, fifth. From fifth, sixth carbon is attached, and from sixth, seventh carbon is attached. 7 is attached to third one. 7 is attached to third one. Now at 7th carbon you may see this is D and deuterium and H, and here also at this one OAC, and this is, so you may write it in this form also. Now let us see the another problem. Okay. Now, so here what should be the product of this reaction under thermal condition? Now, under thermal condition, if you will see the product, then first of all we should give the numbering. The allylic carbon, that should give in number 1. So if this is given number 1, this is 2, this is 3, 4 and 5, and from first another atom, carbon atom is attached. So either this may be given, suppose I have given number 1 dash, or this may also be given number 1 dash. Now which bond breaks in sigmatropic reaction? Which bond breaks? 1 1, that breaks. 1 1 breaks, and it should attach to the 5th position. So how? After getting this energy, so the shift of these pi electron will get started, and this here the valency of this carbon is increased. This bond will break, and this will go over this unsaturated part. From saturated to unsaturated, the shift takes place. So as you can see here, this bond has broken down. This bond has broken down. This is broken, and new bond is formed between 5 and 1 dash. So what you can see, this is, and a 6-membered ring is formed. 1, 2, 3, 4, 5, 6-membered ring is formed over here. So this is the 6-membered ring, and suppose this is our 1 and this is 5, and this is the 1 dash, and this 1 dash our this methyl group is present. And now from 5th you may see this 4th is formed, this is 3, this is 2, like this. Now a new bond is formed between 1st and 2nd, another bond is formed between 4th and 3rd, this would be the case. Now in next, what may happen? Now again we may give the numbering, and suppose here one of the, suppose what I should give. So this is the form, this is the compound which is formed, and now suppose this is the allylic carbon. Again we should see for the allylic carbon, we may see for the allylic carbon, and this is the allylic carbon, and that should give in the number 1, and this is 2, this is 3, 4, 5, and from this allylic carbon you may see one of the hydrogen is present, and this hydrogen, the atom attached to this allylic carbon is also given number 1. Okay, so this 1-1 bond will break again. Again sigmatropic hydrogen shift will take place. So here sigma 1,5 alkyl shift. Here you can see 1,5 alkyl shift has taken place, and here 1,5 hydrogen shift will take place over here. Hydrogen shift will take place over here. Now, so it will shift, with this bond will break, and after this what you will get, this will shift it over this place, and finally so now here double bond, this double bond, now hydrogen is shifted at this place. Now again we may see 1,5 hydrogen shift is possible. 1,5 hydrogen shift is possible. So again we may give, this is our allylic carbon. Okay, this is 2nd, 3rd, 4th and 5th. Again in presence of this heat it will break. So this is 1,1 dash, 1,1 bond will break, and finally what you are getting, you will get this molecule. Okay. New bond, the double bond is formed over here, and here you will have the hydrogen. Okay, so like this is about the 1,3, and this is about the sigmatropic shift, and these are the examples. And in my next lecture I will discuss the Cope rearrangement and various examples of Cope rearrangement. Thank you.